So the next session is dedicated to trainees, and I don't think there's anybody here that would argue we are all trainees. And we have strategically positioned the trainees in order of experience for the next session. And our first trainee is an extremely distinguished investigator who submitted an abstract and was selected based on that distinction. And that is John Hess from the University of Washington, who's going to tell us about bicarb in blood storage. Thanks for joining us, John.
Thank you and good afternoon, and thank you for accepting my abstract. And it's an honor to be here to remember Dr. Bethune, who as a medical student dropped out to go be a stretcher bearer in World War I and went on to become Bethune, the white man of great heart. 600 million people have memorized his eulogy by Mao Zedong. 250 hospitals in China are named after him. I do need to mention that I am the inventor of Additive Solution 7 and the Apex solutions I'm going to be talking about. Don asked the question about 75%. Harry Merriman pointed out that you can store red blood cells for 9 months if you store them at 4% hematocrit and change the additive solution every 4 days. I mean, you're storing them in 5 liters of fluid. This is not a way to make a blood bank. But it does suggest that maybe adding a little bit more solution may make things better. And so I said, what happens when you add a little more additive solution 1? That's what you call SAG-M here in Canada. And what I discovered was the more that you add, the worse the cells do. And I asked if we were poisoning the cells, if we were depriving them of a critical nutrient. And the answer turns out to be both. You're depriving them of phosphate because phosphate passively moves in and out of red cells, and the more solution you put them in, the more moves out and the less able you are to make ATP. And the pH, which is low, will poison phosphofructokinase. And if you make additive solutions that have higher pH and have phosphate in them, the more that you add, the better the cells will store. And so using this kind of logic, we went on and said, what happens if you add a real buffer? And bicarbonate will bind a proton and become carbonate, and then it will dissociate into water and CO2. And the CO2 will diffuse out of the blood bank, just like helium diffuses out of your balloon and it comes down. And so in the upper left corner there, you can see that the more bicarbonate we add, the more diffuses out of the bag. And this means that the pH at all time points stays higher, which means that more lactate gets made. You're actually able to put more energy through the system and keep ATP higher. And this will, in turn, block ATP-dependent storage lesions. Remember, there are many storage lesions. It is not a singular, it is a plural. And so we made Additive Solution 7 using this logic. It was approved in the United States for 6 weeks, bought and buried. We've finally gotten the licenses back, but CE marked for 8 weeks. But at all time points, it provides much better storage of red blood cells. And you can use this in many different ways. It will support warm storage overnight and still allow for 6-week storage, so that if you run a component manufacturing plant, you can close down the evening and night shifts, as they do in many European countries. You can store cells consistently better, so that if you're collecting cells with multiple antigens to transfuse a sickle cell patient, you have more time to keep good cells there and still avoid hemolysis and the iron load that would subsequently come. You can keep cells for 8 weeks and still have them perform better than current 6-week cells. And so there are many uses for better storage. One of them that we recently came across was working with the group of Pavel Seichek at Oxford. He has come up with a way of actually measuring the oxygen offloading rate for red cells. You know, a red cell runs through the lung and in 3 seconds is fully oxygenated. But as oxygen tries to get out of a red cell, it binds to the next unoccupied hemoglobin, and as the red cell membrane and shape change, that path length becomes longer. And it turns out that tau, that oxygen offloading rate, is almost a second in normal cells, and as you make better and better storage solutions, it gets lower and lower because you preserve the morphology, keep the DPG higher, and this works. And now Bill Dumbrell at Cambridge has been using this in isolated, perfused, pre-transplant human kidneys and shown that when you compare old stored cells with fresh cells, that you're able to deliver oxygen better and support renal concentration in the distal tubule better. The first direct human evidence that old red cells actually have a physiologic problem and that better storage prevents it. And so we basically made an additive solution for whole blood. We just took bicarbonate and then some platelet food like guanosine and acetate, put them in a 50 ml bag. And so now when you collect 500 ml of red cells and leukoreduce it, you get the volume down a bit. You can put in 50 ml and still keep it in a 600 ml bag and make it look like the standard product. And we took 30 units of whole blood, made 2-unit pools, split them into 15 pairs, and colleagues at the Hawksworth Blood Center and the U.S. Army Institute of Surgical Research followed them out for 8 weeks with regular sampling. And what we discovered is that hemolysis is less, platelet functionality is maintained out to the 8 weeks. And we say this in terms of the TEG maximum amplitude is maintained. You can break the TEG maximum amplitude down into the fibrinogen component, and then the rest of it is the platelets pulling the fibrinogen net tight. And half of that is maintained all the way out at 8 weeks, pointing out that platelets store very well in the presence of red cells at reasonable pHs. And all of this data is just been released in early release online and is published in Transfusion. And so let me stop there and take any questions. Yes.
Thanks for the talk. How did you determine that the morphology of the red blood cells changed less with these other additive solutions?
Well, the way that Dr. Svitek has done that is to use forward and side scatter. And, as the red cell changes shape, it also becomes bumpy. And, by using the ratio of side scatter to forward scatter, he has something he's called the flow scan. And they're presenting all this data in May at Milan at the ISBT meeting.
Yeah, thank you. So that's an aggregate cell measurement, right? It doesn't look at the proportion of
Now, what
cells?
Svycek initially did was took oxygenated red cells at a very low concentration and blew them into an override of deoxygenated water, and then photographed them and watched the color change, tracking individual cells to produce tau. And basically shows that although you can load the oxygen on a red cell in 0.003 of a second, it takes a second to unload it.
Thank you very much.
Yes. Claudia.
Thanks for a really nice talk, John. The platelet function appears to be preserved.
Yes.
There are a lot of people saying, we'll give whole blood and we'll throw in a unit of platelets because after 21 days of storage, the platelets are probably junk. If they're stored in AS7, you're saying that that would not be the case?
We have, well, nobody's ever received it. It's not FDA licensed, you know. You promptly get into vicious circles when you, try and take lab stuff to clinical work. And more than that, how do you prove that a platelet product works? I mean, we know that they maintain counts. We have gone back into the 300,000 units of blood that were transfused in the wars in Southwest Asia and managed to find those 600 units of cold stored platelets and match them to 4 to 1 to people who got regular platelets, and then gone through the database and matched them and shown that the people who got the cold stored platelets didn't do any worse than the people who got, you can sort of come up with fantastic ways to sort of suggest that platelets work, but actually measuring it is quite difficult.
Thank you.
Thank you very much.